Would anyone want to be invisible? If the answer is yes, here is how. Here is the overview. The Magnetic Invisibility Suit, MIS, is a speculative wearable technology designed to achieve 360-degree optical invisibility by manipulating light using magnetic fields. Inspired by the Rochester cloaking device, which uses lenses to bend light around an object, the MIS employs advanced metamaterials and magnetic field manipulation to capture and redirect light from one side of the wearer to the other, projecting it into thin air to create the illusion of transparency in all directions. Here is the conceptual mechanism. The suit leverages the following principles. Metamaterial surface. The suit is coated with a flexible, nanoscale metamaterial layer engineered to interact with magnetic fields and light. These metamaterials have a negative refractive index, enabling precise control over light paths. Magnetic field projection. Arrays of microelectromagnets embedded in the suit generate dynamic, spatially varying magnetic fields. These fields manipulate the metamaterials to bend light around the wearer. Light capture and projection. Photonic sensors capture incoming light, intensity, wavelength, and polarization from all directions. The suit processes this data and uses the magnetic fields to guide light to the opposite side, where it is emitted to mimic the background. Thin air display. The magnetic fields create localized regions of ionized air, plasma, that act as transient screens for light projection. These plasma regions scatter the redirected light to create a seamless visual effect. Here are the components. 1. Metamaterial skin. Material. Flexible, graphene-based metamaterial with tunable optical properties. Function. Responds to magnetic fields to alter its refractive index, bending light around the wearer. Thickness. 100 nanometers, ensuring flexibility and wearability. Properties. Negative refractive index, -1 to -2, at visible wavelengths, 400 to 700 nanometers, controlled by magnetic field strength. 2. Microelectromagnet array. Design. 10 to the power of 6 microelectromagnets per square meter, embedded in a flexible carbon nanotube mesh. Power source. Thin film lithium-ion batteries, 50 watt-hours per kilogram, integrated into the suit, providing 24-hour operation. Control. Onboard quantum processors, 10 to the power of 12 flops, calculate real-time magnetic field configurations to achieve desired light paths. Field strength. 0.1 to 1 Tesla, locally adjustable to manipulate metamaterial properties. 3. Photonic sensor network. Sensors. 10 to the power of 8 nanoscale CMOS cameras per square meter, capturing light data, intensity, wavelength, angle. Processing. Edge AI processes sensor data to map the 360-degree light field around the wearer. Resolution. 4K equivalent per 10 square centimeters, ensuring high-fidelity light capture. 4. Plasma projection system. Mechanism. Magnetic fields ionize ambient air molecules to create transient plasma regions, density approximately 10 to the power of 15 particles per cc. Function. Plasma scatters redirected light to form a screen in thin air, 1 to 10 centimeters from the suit's surface. Control. Magnetic field gradients shape plasma regions to align with light emission points. Energy cost. 100 W per square meter for plasma generation, sustained by the suit's power system. Here is the operational workflow. Light capture. Sensors detect incoming light from all directions, creating a 360-degree light field map. Data processing. Quantum processors compute the required light paths to make the wearer appear transparent. Magnetic field adjustment. Microelectromagnets generate precise magnetic fields to tune the metamaterial's refractive index. Light redirection. Metamaterials bend light around the wearer, guided by magnetic fields, to the opposite side. Projection. Redirected light is emitted into plasma regions, which scatter it to match the background, creating the illusion of invisibility. Here are the technical challenges. Magnetic field precision. Achieving sub-micron control of magnetic fields to manipulate light accurately. Power consumption. High energy demands for plasma generation and electromagnet operation, estimated 500 W total. Thermal management. Dissipating heat from electromagnets and processors using microfluidic cooling channels. Latency. Real-time processing of 360-degree light data requires ultra-low latency, less than 1 millisecond. Material durability. Ensuring metamaterials and sensors withstand wear, bending, and environmental factors. What are the limitations? Range of invisibility. Effective only in visible spectrum, 400 to 700 nanometers, IR or UV may reveal the wearer. Environmental dependence. Plasma projection requires sufficient ambient air, ineffective in vacuum or low-pressure environments. Size and weight. Suit thickness, approximately 1 centimeter, and weight, approximately 5 kilogram, may limit mobility. Background complexity. Highly dynamic backgrounds, e.g., crowds, may cause visual artifacts due to processing delays. What are some safety considerations? Magnetic field exposure. Fields are localized to avoid biological effects, with exposure below 0.01 Tesla at skin level. Plasma safety. Plasma regions are low energy and short-lived to prevent burns or electrical hazards. Fail-safe. Automatic shutdown if power or processing failures are detected to prevent visual glitches or overheating. Potential future improvements include broadband cloaking. Extend functionality to IR and UV spectra using multi-band metamaterials. Energy efficiency. Integrate solar or kinetic energy harvesting to reduce battery reliance. Adaptive AI. Improve background prediction for dynamic environments using deep learning. Ultimately, the magnetic invisibility suit represents a fusion of advanced metamaterials, magnetic field manipulation, and photonic technologies to achieve 360-degree optical invisibility. While theoretically feasible with future advancements in materials and computing, significant engineering challenges remain. This design provides a foundation for further research and development in active cloaking technologies. Now it is time for the actual magnetic invisibility suit creation process. This document provides a detailed, step-by-step guide to creating the magnetic invisibility suit, MIS, a speculative wearable technology that achieves 360-degree optical invisibility using magnetic fields, metamaterials, and plasma projection. The process is divided into material synthesis, component fabrication, suit assembly. Phase 1. Material synthesis. Step 1.1. Synthesize graphene-based metamaterial. Objective. Create a flexible, graphene-based metamaterial with tunable negative refractive index, -1 to -2, for visible light, 400 to 700 nanometers. Process. Graphene growth. Use chemical vapor deposition, CVD, to grow single-layer graphene on a copper substrate. Equipment. CVD furnace, Eichstron Black Magic. Conditions. 1000 degrees Celsius, methane, carbon tetrahydride, flow at 50 sccm, hydrogen, H2, at 20 sccm, pressure 0.1 millibars. Duration. 60 minutes to achieve uniform 1 nanometer thick graphene sheets. Metamaterial structuring. Transfer graphene to a flexible polyimide substrate, 100 micrometers thick, using wet transfer, PMMA coating, copper etching with iron 3 chloride. Pattern graphene into nanoscale split ring resonators, SRRs, using electron beam lithography. SRR dimensions: 100 nanometers diameter, 10 nanometers gap, 50 nanometers spacing. Etch with oxygen plasma, 50W, 30S, to define SRR patterns. Deposit 5 nanometers titanium dioxide, titanium 4 oxide, layer via atomic layer deposition, ALD, to enhance optical tunability. Doping for tunability. Dope graphene with nitrogen, N2, via plasma-enhanced CVD to adjust electron density. Conditions. 300 degrees Celsius, 10 sccm N2, 5W plasma power, 10 minutes. Verify doping with Raman spectroscopy, D-G ratio approximately 0.1. Quality control. Inspect with scanning electron microscopy, SEM, for SRR uniformity. Measure refractive index using ellipsometra, target. -1 to -2 at 550 nanometers. Output. 1 square meter sheets of flexible metamaterial, 100 nanometers thick. Duration. 7 days per batch. Step 1.2. Fabricate carbon nanotube, CNT, mesh for electromagnet array. Objective. Create a flexible CNT mesh to support microelectromagnets. Process. CNT synthesis. Use catalytic CVD to grow multi-walled CNTs, MWCNTs. Catalyst. 5 nanometers iron, Fe, nanoparticles on silicon substrate. Conditions. 700 degrees Celsius, acetylene, dicarbon dihydride, at 30 sccm, 30 minutes. CNT dimensions. 10 nanometers diameter, 100 micrometers length. Mesh formation. Disperse CNTs in ethanol via ultrasonication, 100 W, 10 minutes. Spin coat onto polyimide substrate, 500 revolutions per minute, 30 s. Anneal at 400 degrees Celsius in argon to form a 50 micrometers thick mesh. Functionalization. Coat with 10 nanometers silicon oxide via ALD for insulation. Verify conductivity, less than 10 ohms per centimeter, using a 4-point probe. Output. 1 square meter CNT mesh, 50 micrometers thick. Duration. 5 days per batch. Step 1.3. Prepare thin film battery materials. Objective. Synthesize materials for flexible lithium-ion batteries. Process. Anode preparation. Mix graphite powder, 95 Wt%, PVDF binder, 5 Wt%, in NMP solvent. Coat onto 10 micrometers copper foil using a doctor blade, 100 micrometers wet thickness. Dry at 120 degrees Celsius for 2 hours. Cathode preparation. Mix LiCo O2, 90 Wt%, carbon black, 5 Wt%, PVDF, 5 Wt%, in NMP. Coat onto 10 micrometers aluminum foil, 100 micrometers wet thickness. Dry at 120 degrees Celsius for 2 hours. Electrolyte. Prepare solid-state electrolyte, lipin, via RF sputtering. Conditions. 200 W, 5 mTORR, nitrogen atmosphere, 4 hours. Thickness. 1 micrometer. Quality control. Test capacity, target, 50 watt-hours per kilogram, using galvanostatic cycling. Verify flexibility by bending, radius less than 1 centimeter, without cracking. Output. Battery films, 50 micrometers thick, 1 square meter. Duration. 4 days per batch. Phase 2. Component fabrication. Step 2.1. Fabricate micro-electromagnet array. Objective. Create 10 to the power of 6 micro-electromagnets per square meter on CNT mesh. Process. Coil patterning. Deposit 100 nanometers copper layer on CNT mesh via sputtering. Pattern into 50 micrometers times 50 micrometers spiral coils, 5 turns, 1 micrometer line width, using photolithography. Etch with ammonium persulfate, 0.1 m, 30 s. Magnetic core. Deposit 10 micrometers iron nickel, Fe, alloy core in coil centers via electroplating. Conditions. 1 A per square decimeter, 10 minutes. Insulation. Coat with 1 micrometer parylene C via CVD for electrical insulation. Testing. Measure field strength, target. 0.1 to 1 T at 1 mm, using a Hall probe. Verify coil density with optical microscopy. Output. Electromagnet array on CNT mesh, 60 micrometers thick. Duration. 6 days per square meter. Step 2.2. Fabricate photonic sensor network. Objective. Create 10 to the power of 8 nanoscale CMOS cameras per square meter. Process. Sensor fabrication. Use a 7 nanometer CMOS process on silicon wafers. Pattern 1 micrometer times 1 micrometer photodiodes with bare filters for RGB detection. Etch with deep reactive ion etching, dry, 100 nanometers precision. Integration. Transfer sensors to a flexible polyimide substrate using laser lift-off. Bond with 10 nanometers gold interconnects via flip chip bonding. Testing. Verify resolution, 4K per 10 square centimeters, using test patterns. Measure sensitivity, 400 to 700 nanometers, greater than 80% quantum efficiency. Output. Sensor array, 50 micrometers thick, 1 square meter. Duration. 10 days per square meter. Step 2.3. Fabricate quantum processors. Objective. Create quantum processors for real-time light field processing. Process. Qubit fabrication. Use superconducting qubits, transmons, on silicon substrate. Deposit 100 nanometers aluminum for Josephson junctions via E-beam evaporation. Pattern with electron beam lithography, 10 nanometers resolution. Control circuitry. Integrate microwave resonators, 5 GHz, for qubit control. Add 50 nanometers niobium interconnects via sputtering. Cooling integration. Embed microfluidic cooling channels, 10 micrometers diameter, with liquid nitrogen circulation. Testing. Verify performance, 10 to the power of 12 flops, using quantum benchmarking, e.g., randomized benchmarking. Ensure latency less than 1 millisecond for light field processing. Output: quantum processor chips, 1 square centimeter each, 100 units per square meter. Duration: 14 days per 100 chips. Phase 3. Suit assembly. Step 3.1. Layer integration. Objective: assemble metamaterial, electromagnet array, sensors, processors, and batteries into a flexible suit. Process: base layer. Use a 500 micrometers neoprene base for comfort and durability. Cut to fit the human body, standard sizes, S, M, L, using laser cutting. Battery layer. Laminate battery films onto neoprene using thermal bonding, 120 degrees Celsius, 10S. Connect to the power bus with 10 micrometers copper traces. Electromagnet layer. Bond CNT mesh with electromagnets to the battery layer using epoxy. Cure at 80 degrees Celsius, 1 hour. Connect to the power bus with 50 micrometers vias. Sensor layer. Attach a sensor array using adhesive film, 10 micrometers thick. Connect to processors with 100 nanometers gold interconnects. Processor layer. Mount quantum processor chips in a grid, 10 centimeters spacing. Integrate cooling channels with inlet-outlet ports. Metamaterial layer. Bond metamaterial skin as the outer layer using UV curable adhesive. Ensure alignment with electromagnets, tolerance less than 1 micrometer. Encapsulation. Coat the entire suit with 10 micrometers Parylene C for environmental protection. Output: assembled suit, approximately 1 centimeter thick, approximately 5 kilogram. Duration: 7 days per suit. Step 3.2. Electrical integration. Objective: connect all components electrically. Process: power distribution. Route power from batteries to electromagnets, sensors, and processors via 50 micrometers copper bus. Add 100 nanofarads capacitors for noise suppression. Data bus. Use 10 micrometers graphene interconnects for high-speed data transfer, 10 gigabits per second. Connect sensors to processors via I2C protocol. Control interface. Embed a central control unit, ARM Cortex-M7, 600 MHz, for system coordination. Add wireless module, Wi-Fi 6, 2.4 GHz, for diagnostics. Testing. Verify power delivery, 500 W total, using multimeter. Test data transfer with diagnostic software. Duration: 3 days per suit. Phase 4. Software development. Step 4.1. Develop light field processing software. Objective: create software to process 360-degree light field data and control light redirection. Process: sensor data acquisition. Write Python code, using NumPy, to collect RGB data from 10 to the power of 8 sensors. Sampling rate: 60 Hz. Light field mapping. Implement ray tracing algorithms to map incoming light paths. Use CUDA for GPU acceleration on quantum processor adjuncts. Magnetic field control. Develop control algorithms to adjust electromagnet currents, 0 to 1A, based on light paths. Use inverse Maxwell equations to compute field gradients. Plasma projection. Write code to modulate magnetic fields for plasma generation, 10 to the power of 15 particles per cc. Optimize for 1 to 10 centimeters projection distance. Latency optimization. Parallelize computations across 100 quantum processors. Target latency: less than 1 millisecond per frame. Output: firmware, 10 megabytes, flashed to control unit. Duration: 14 days. Step 4.2. Safety and fail-safe protocols. Objective: ensure safe operation and error handling. Process: magnetic field limits. Program limits to keep skin level exposure less than 0.01 T. Use real-time feedback from Hall sensors. Thermal management. Monitor temperature with 1000 thermistors per square meter. Shut down if temperature exceeds 50 degrees Celsius. Power fail-safe. Implement automatic shutdown if battery voltage drops below 3V. Testing. Simulate failures, power loss, sensor dropout, to verify shutdown. Output: safety firmware module, 1 megabyte. Duration: 5 days. Phase 5. Testing and calibration. Step 5.1. Component testing. Objective: verify individual component performance. Process: metamaterial. Test refractive index tunability. -1 to -2, with varying magnetic fields, 0.1-1 T. Use laser interferometry, 532 nanometers. Electromagnets. Measure field strength and uniformity across 1 square meter. Target. 0.1 to 1 T, less than 1% variation. Sensors. Test light capture, 400 to 700 nanometers, under varying illumination, 10-10,000 lux. Verify 4K resolution per 10 square centimeters. Processors. Benchmark with synthetic light field data, 10 to the power of 12 flops. Duration. 7 days. Step 5.2. System integration testing. Objective. Verify suit functionality as a whole. Process. Static background test. Place suit in a controlled environment, uniform white background, 1000 lux. Verify invisibility from 10 viewing angles, 0 to 360 degrees. Measure visual artifacts using high-speed camera, 120 fps. Dynamic background test. Test with moving background, e.g., scrolling pattern at 1 meter per second. Assess latency and projection accuracy. Plasma projection. Verify plasma screen formation, 1 to 10 centimeters from suit. Measure light scattering efficiency, greater than 90%. Duration. 10 days. Step 5.3. Field testing. Objective. Test suit in real-world conditions. Process. Outdoor testing. Test in daylight, 5000 lux, and low light, 10 lux, conditions. Verify invisibility against complex backgrounds, trees, buildings. Mobility testing. Have wearer walk, run, and bend to assess flexibility and durability. Monitor for material fatigue using strain gauges. Safety testing. Measure magnetic field exposure at skin, less than 0.01 T. Monitor thermal output, less than 40 degrees Celsius at skin. Duration. 14 days. Phase 6. Final assembly and delivery. Step 6.1. Final calibration. Objective. Optimize suit performance for specific user. Process. Fit adjustment. Tailor suit to user's body using laser scanning, 0.1 mm precision. Adjust neoprene base for ergonomic fit. Software calibration. Calibrate light field mapping for user's environment, e.g., urban, rural. Update firmware with user-specific parameters. Final inspection. Verify all components, sensors, electromagnets, batteries, are operational. Conduct full invisibility test, 360 degrees viewing angles. Duration. 3 days. Step 6.2. Packaging and documentation. Objective. Prepare a suit for delivery. Process. Packaging. Place suit in a vacuum-sealed, ESD-safe container. Include charging unit, wireless, 100W, and user manual. Documentation. Provide detailed user guide, PDF, covering operation, maintenance, and safety. Include troubleshooting guides for common issues, e.g., sensor dropout. Duration. 2 days. Timeline and resources. Total duration. Approximately 91 days, 3 months, for one suit, assuming parallel processing of components. Personnel. Materials scientists. 5, for metamaterial and CNT synthesis. Electrical engineers. 5, for electromagnet and sensor fabrication. Software engineers. 3, for firmware and control algorithms. Technicians. 5, for assembly and testing. Equipment. CVD furnace, electron beam lithography, ALD system, RF sputtering, laser cutter, SEM, ellipsometer, Hall probe, high-speed camera. Cost estimate. $10 million per suit, materials, labor, equipment, assuming prototype scale production. It is important to note, scalability. Mass production could reduce costs by 50% with optimized manufacturing. Limitations. Suit is limited to visible spectrum. IR, UV cloaking requires further metamaterial development. Safety. Strict adherence to magnetic field and thermal limits is critical to prevent user harm. This process outlines the creation of a single magnetic invisibility suit. Iterative improvements and testing will be necessary to achieve practical deployment.